Hello, Tracing Summit. My name's Dom. I'm an engineer at New Relic working on the Pixie open source project, and I'm excited to talk to you today about reliable user space TLS tracing with eBPF. The Pixie open source project, so just to give it a brief introduction, it's a observability tool for Kubernetes powered by eBPF, and one of its core features is providing full fidelity protocol traces between your microservices. And so we're able to show you all of the gRPC, HTTP, MySQL, and other protocol traffic happening on your cluster. And the reason why we want to tackle tracing TLS connections is because of how widely adopted TLS is becoming in today's environments. And in the case where we can't see the data, there's substantial blind spots, not only for Pixie, but other observability tools as well. At the bottom of this slide, you can see a picture of Pixie's UI, and what this visualization is showing us is all of the HTTP traffic happening on this particular cluster. So to give a brief overview of what we'll be discussing today, we're first going to go over TLS tracing and get an understanding for why handling user space is unavoidable. We'll then do a deep dive on Pixie's initial form of TLS tracing and talk about the challenges that we faced. From there, we'll talk about our new implementation of tracing and how it handles some of these complexities, and then we'll go on to discuss where we see future work in this space. So, moving on to TLS. So, encryption occurs within user space libraries. If you're familiar with things like OpenSSL or BoringSSL, this is the layer where it occurs. If we look at the left-hand side of this visualization, we'll see what an application that doesn't use TLS looks like and how we can trace it with eBPF. The application itself is calling the send and receive syscalls with the network payload directly. And so we're able to attach a K-probe here to trigger, capture the payload, and do our user space processing from there. Now, if we look at the TLS case, by the time the send and receive syscalls occur, the data is already encrypted. So we have to hook into an earlier point of the life cycle. And so where this occurs is within the SSL write and SSL read functions within the TLS library. So hopefully you can see here that tracing user space is a necessity. And so with eBPF, we're able to add uprobes here and gain access to the plain text again. While Pixie does this, this is also a similar tactic to what other tools like sslsniff do from BCC tools. So now we have that overview. So while triggering on those functions gives us access to the plain text, in reality, production systems come with more challenges. The TLS libraries can be linked in different ways. There's also a variety of popular libraries, and ideally we'd be able to cover as many use cases as possible. And even how you use the TLS library can create tracing challenges, which we'll talk more about later. So just accessing the plain text is just part of the story. When we're trying to surface how your microservices are behaving in production, we need metadata to make this data usable. So, talking more about the challenges, like I mentioned, protocol data is just part of the story. We actually need to be able to tell where the network traffic occurred from, and so we need some form of connection identity in order to make it usable. And so the way Pixie accomplishes this is through using socket file descriptors for that connection identity. So in this example here, you can see that service C is making 2 HTTP requests to service A. We need to be able to make sure we keep these payloads separate and we don't match requests and responses against the wrong request. So going back to our plain text case, the socket file descriptor is easily accessible because it's part of the syscall contract. If you look at the send function signature below, you can see that the socket FD is the first parameter here. Unfortunately, for these SSL libraries, the socket file descriptors aren't part of that contract, and so we have to provide another mechanism to do this. you can see the SSL write function signature here. And so you can see the plain text is accessible, but the file descriptor is not part of that. And so the way Pixie's initial form of TLS tracing accomplished this is by walking that SSL struct, that's the first argument. Within that structure, there's a BIO member, and within that BIO member, oftentimes the socket file descriptor will be stored in this num field. So let's dig in a layer deeper on how that works. So on the right-hand side here, you can see kind of a visualization of how this SSL struct is laid out in memory. In order for us to make it to the socket file descriptor, we need 2 offsets to make this possible. So we need to first get to the RBIO member, and then if we follow that pointer, we then need the distance between the start of the BIO struct to the socket file descriptor. And so Pixie's first style of tracing, basically we went and calculated these offsets, but since we're tracing user space, there's no guarantees that these offsets are stable. And so the assumption that we made in order to make this style of tracing work is that for every version of OpenSSL that we supported, we assumed that the offsets would be stable. Now, this sort of creates an additional challenge. We now also need to reliably detect the OpenSSL version in use. For our initial implementation, what we did is there's another function available within OpenSSL called OpenSSL version num, and that is what we relied on for returning the version, and then we could conditionally apply our offsets from there. This worked initially, but as we wanted to support more libraries and more linking options, it started to become more and more challenging. So we're going to focus in on OpenSSL version detection and each of the scenarios that we were trying to support. So for the dynamically linked OpenSSL case, we have the shared objects that contain the 3 functions of interest. I mentioned before that we would rely on this version num function to get the version, and so we were very easily able to use dlsim to get a function pointer, and from there the version detection was possible, or we could apply the offsets for that particular version. One of the next use cases we supported was Netty TC native. Netty is a networking library in Java, and it has this TC native component that is native code doing the encryption. And so the shared object we needed to trace was libnetty TC native. Now in this case, the OpenSSL version num symbol was not a public symbol like in the previous case. And so our dlsim method from before did not work. And so we had to develop a way to find the raw memory address of where this function exists, which we call our raw symbol to function pointer. And from there, we were able to call that random memory address, get the version, and proceed from there. The use case we wanted to support after that was statically linked OpenSSL and BoringSSL. Now, these symbols don't exist, they're directly embedded within the application. The OpenSSL version num function that we were using before, there's no guarantee that this function will exist, because if the application doesn't call this function, the linker won't leave it within the executable. And so there was one challenge there that it's like our indicator was just no longer present, but also BoringSSL has an added layer of complexity where it's sort of in a rolling release style where when you compile your application, you're just using whatever the latest commit from main you're pulling in. And so it doesn't really have a concept of versioning. So even if this symbol was available, we felt like it was going to be hairy moving forward because there isn't a concept of versioning, essentially. And so, yeah, neither of our things worked. So we kind of went back to the drawing board, and we wanted to think of a redesigned solution. As we started adding more and more use cases in scope, we started to realize the challenges that were piling up. And so we started to wonder, maybe we're not solving the right problem. Relying on these user space offsets with very little stability guarantees already had, difficulties with it, and now, there's just more and more things we're trying to solve. And so we wanted to kind of take a step back and sort of classify the integrations of these TLS libraries and see if that could kind of help us understand what we were trying to tackle. So there's sort of two main classifications that we have. There's BIO native, and BIO it stands for basic input output, but it's OpenSSL's concept for it doing I/O. And so BIO native means that OpenSSL is going to be managing the I/O for the socket for you. And so these are the cases where, just like what we saw with that SSL struct, the socket FD will be populated within it. And some examples of applications that fit this mold are Nginx and Python. The other classification is custom BIO, and this is where OpenSSL is used solely for encryption, and the application itself handles I/O, and it's usually done in an asynchronous fashion. And examples of this variant are Node.js and Envoy. So now that we kind of know these classifications, let's take a look at them side by side and see how they work. So as I mentioned before, BIO native OpenSSL is handling the socket I/O for us. And so we see that all of the syscalls, send and receive, originate from the OpenSSL library. In the custom BIO case, the application is receiving the ciphertext from the TLS library and then later calling send and receive. And so as we kind of thought more about these cases, we were wondering if there were assumptions that we could make about the call stack on the cases on the left, because these BIO native cases were the ones that Pixie already supported. And so when we were thinking about this redesigned solution, we really needed to have the same coverage of tracing. We needed to solve for this left case. And so I want to dive through an example and just kind of look at the call stack over time and where we saw opportunity for changing this. So we're going to imagine that we have a HTTP service that when it handles an HTTP request, it will query a database over a TLS connection. So the first thing the query_db function call will do is try and write its query to the TLS connection, and so SSL write will be called. From there, we'll have write syscalls occur. And so this write syscall layer was where we were previously accessing the socket FD in the plaintext case. And so because of the way BIO native is and the user space function and the syscall are on the stack at the same time, we thought there was an opportunity to pass the syscall back to our instrumentation on the user space function. So what our assumption was is that for BIO native applications, these socket syscalls will occur while those functions are on the stack, and that would provide an opportunity for us to pass the socket FD from this nested syscall back to our user space return probe. And the potential here is that we could hopefully remove our reliance on any user space offsets and avoid the ongoing maintenance that we had with our existing form of tracing. Now, one thing to mention is we weren't looking for an assumption that was universally true. We know there are some cases that wouldn't fit this mold. For example, OpenSSL has the ability to perform async operations through its engine interface. And so, for instance, you can do hardware offload for TLS for cases that look like they're BIO native. And so we were basically just looking to replace what coverage we already had, and these hardware offload cases wouldn't have worked with Pixie's previous form of tracing. So this implementation really relied on the fact that we were correct about being able to make these assumptions about the call stack. And so what our primary concern is that there could be unrelated I/O or syscalls occurring while the TLS libraries are still on the stack. And so in order to gain confidence in this solution, we developed an integrity checking mechanism. And this initially, we viewed it as just like an experiment, but it later turned into a core part of our TLS tracing implementation. And so essentially what it does is when a syscall occurs, we basically validate that if we had seen an FD before, that it remains the same FD. we didn't want to see a case where the socket file descriptors were switching. And so it is okay for the syscall to occur multiple times, because you could have situations like buffered writes where you only write a portion of the payload and a syscall for the same socket FD happens later. But we just need to make sure that the file descriptors remain the same. And so we ran this integrity checker in, so I mentioned it's part of our tracing implementation, so it's always on. But over the 6 months that we've ran this, we've only found 5 programs that violate this assumption. The clusters that do see this condition essentially belonged to the same set of end users because they were running the same processes on these clusters. And the overall volume of these occurrences are extremely low. And so we gained confidence in that we could perform this, this tracing in this way from running this in production and seeing the results. So now that we've gotten that background out, I want to kind of walk through how our tracing works and what BPF probes are firing as it's occurring. So we're going to return to our fictitious HTTP service that queries a database. And so as the SSL write frame gets pushed onto the stack, our first BPF probe is going to trigger. And what that SSL write entry probe does is it stores in a BPF map a key value pair where the key is the current PID TGID and the value is an invalid FD sentinel value. This is essentially just an indicator that the TLS library function call is not now on the stack. From there, our write syscalls will occur. And this is also where the integrity checking happens. And so we basically look up to see if that PID TGID key value pair is present, and if it is, we will update it to the value of the socket FD that we got from the syscall. The reason why there's entry/return here is because for the write syscall, it could be file IO or something else, and Pixie has a way to identify if it's socket or a socket syscall or not. So we defer those ones to the return probe where that filtering mechanism is present. But if it's a socket-specific syscall, we do it on the entry probe. From there, the write syscall will return. And then when the SSL write frame is about to pop off the stack, our final probe will trigger. And what happens here is we check to see that key value pair in the BPF map. If the value is no longer that sentinel value, we will send the payload to our perf buffer, where Pixie's user space component will pick up from there and do its protocol tracing. So hopefully this shows a good view of how we are working around the need for relying on those user space offsets and getting access to that stable interface that we used in the plaintext case. So now that we've seen how the tracing works, I wanted to show you how our tracing coverage has changed as a result of this. So Pixie's initial implementation supported OpenSSL v1.1.0 and 1.1.1. OpenSSL v3 was not supported, but our tracing would have been compatible with it as long as we did the work to identify the user space offsets. With our redesigned implementation, we have coverage across all of these OpenSSL versions in addition to future ones. And so, if OpenSSL v4 comes out, our tracing will work with no additional code changes. We also were able to trace statically linked BoringSSL and OpenSSL. And this is an area where our previous form of tracing could not have worked. And the reason for this is the BoringSSL release style, where it's a rolling release, and you can't really get a very strong indicator for versioning. And so if the offsets ever changed, we would have no way to reliably detect that. Now, as we look for the future, Pixie supports a few of the custom BIO cases like Node.js and NetETC native. However, they rely on application-specific tracing. And so the maintenance of this is even higher than the OpenSSL dynamic tracing, the initial implementation. And so this is an area where I see a lot of potential for us trying to engineer a solution that would be more maintainable and also give us broader coverage if we can handle these custom BIO cases in a better way. So with that, I mentioned, so looking to the future, we want to better support custom BIO use cases. It would be great if we could remove these application-specific forms of tracing, and ideally we would get broader coverage across all applications, things like Envoy, Istio, et cetera. Another area we would like to investigate is handling statically linked cases where the symbols are completely stripped. The new form of tracing would be compatible with these, but the issue is we don't know the memory address of where to attach our BPF probes. And so I don't think this is an easy problem to solve, but if we were somehow able to watch a process and learn over time that maybe SSL write and SSL read exist in these places, and we could attach the probes later on, our new implementation could support use cases like this. And with that, I want to thank you for attending my talk, and I'm happy to answer any questions you have.
Question from the audience? Start with Nick.
Can I just annoy you by pointing out that if you'd built OpenSSL with binutils 2.35 or above and compiled with -GCTF, you would have had a complete view of the entire type graph of OpenSSL and could just have walked to, to the in and out BIOS with no trouble at all and no need for hardwired offsets, and it supports statically linked binaries as well. Sorry.
So the issue with that is our end users just deploy our application on their Kubernetes cluster. And so we're at the mercy of whatever customers are running. And so when they say you support TLS tracing, but you don't support my application, like we effectively have done nothing for them. And so we have to handle just whatever's available there.
Okay, in that case, your next problem is, what about FD recycling? You can't just check an FD and hope that an FD number corresponds to the same underlying file description. They get closed all the time.
We have so the BPF programs that we talked about are just a subset of what Pixie does. We hook into the closed syscall, and so we do handle kind of the life cycle of these things. So I mean, if our K probe were to not fire, then there's a potential issue there, but I believe like for the majority of the Happy Pass cases, that would be handled.
Thank you. Mathieu?
Maybe you have considered that approach, but one way that I think could solve pretty much all your problems would be to use the encrypted bytes as a match string. So what you could do is, in the TLS write function, so you get your plaintext, you can find a way to gather the encrypted result, and either hash that result or use it as is for a comparison, and use that to compare in your eBPF hash buckets to figure out, oh yes, okay, so, and then hijack, let's say, a libc write in user space, rather than going for a system call which may receive byte per byte, or you don't know, but usually libc write will be called in a single call for the entire, let's say, thing to send out. So then you can compare by encrypted hash and figure out, do the matching, okay, this is the plaintext that belongs to this file descriptor that is being written to by libc. So using the hash would fix all your problems without having to dig into internal data structures of the application. It would handle even the asynchronous case where you do the write later, if you even do the write from a different thread, if you have work queues or whatnot, it just works.
That isn't something that we've considered or investigated, but that's really good thing for us to look into.
Other questions? I do have a few. I missed some part of the talk, so perhaps that's why I have these questions. But so from my understanding, the biggest problem that you had is to figure out the file descriptor to associate it with the information that you're capturing to get some context. Why not just determine the file descriptor when you're allocating this SSL structure and map the user space address to this file descriptor instead, and also probe when the structure is destroyed by the library and then undo the mapping of the file descriptor? That should be doable, no?
So you're saying add more tracing to these TLS libraries and catch where...
Yeah, but then you don't have to trace syscalls like write and read to determine the file descriptor. So you remove trace points, you move them when you're creating and destroying.
So that would work for the case where the TLS library is doing the write. It knows about the file descriptor, but it does not work for the case where it's sending back the encrypted text message to the application, and then the application sends it over.
So to the point on adding more tracing to the TLS library, I don't know that we've considered that specific approach, but when we were trying to determine if we could get version information out of BoringSSL, I think the more you probe the TLS library, the more difficult it becomes for that to work on multiple ones. Like right now, we cover BoringSSL and OpenSSL, and let's say GNU TLS has similar functions, but they're named something differently. As long as we attach to the write and read functions, I believe this should still work. But if we start tracing where these objects are created, then we kind of have to become a little bit more of an expert on that library and understand the use case really well, and make sure there aren't gaps in us missing things. Because there are some different functions. You can sort of create the BIO struct yourself and populate it, and then you can pass it to OpenSSL. Or you can say, give me a buffer, like an SSL struct with the buffers already hooked up. And so we felt that it was just like we were really having to vet our understanding of the TLS library. And so we tried to go for kind of interfaces that felt a little bit more stable and like the same, if that makes sense.
Okay. And I'm just wondering, is there any performance problem considering that you're probing SSL write and read, which could be buffered, and the application could do a lot of write or read, and you're using uprobe for that, so that's a lot of overhead.
There's definitely overhead. I mean, we're introducing a context switch. I don't know all of the kernel side of things incredibly detailed, but I believe, once we hit that function, we have to switch into kernel space, and then the BPF program runs. So there is overhead here. We believe it's there's a cost to it, but we think that the value of the, understanding your services in your cluster is worth it in those cases.
I'd be more concerned about the added overhead of syscall tracing, because as soon as it gets enabled in the kernel, it's basically enabled for everyone. Every system call is taking a hit. So that's really not cheap.
Yeah, and it will be also possible to do a user space solution for the SSL write and read portion. If you LD preload, for example, a wrapper of this function, and you can just enable it, disable it using some way. It will be possible to avoid the uprobe for that, but for the syscall, Mathieu is right. It's impacting the whole system. So. And the last question is, did you have any concern about security? Since this is a security measure, and you're basically bypassing it. So I see some hold in there.
Naturally, as we've talked with people who want to use Pixie and are interested in the project, when you tell them that we can see data that's encrypted, it naturally makes them uncomfortable in some cases. I do think BPF is privileged, and so we do have the verifiers. There is sandboxing and verification done on the BPF program. So I kind of think when you have root level access, at least in this case, it's scoped to the BPF program. There are, we store the data on each node, so the data doesn't leave. The way Pixie works is there's sort of this distributed architecture where when you go to query for data, it actually fans out your request, and only queries the nodes running that specific service. And so your unencrypted data doesn't leave that node. I do think there's like probably more hardening and access control things we can do, but from the BPF side, you know, the program's verified and, you know, as well scoped as I think it can be. And so, yeah, I understand the concern, and I think there's more work to be done there.
Yeah, it transformed data that is normally just sitting temporarily in memory and being overwritten into something that can be kept on storage. Even if it does not leave the node, it's the node storage. And I suspect the requirements for privacy might be different. So this is really something important to keep in mind.
Yeah. The service is an in-memory data store. We don't write anything out to disk, but yes, you're right that it is longer lived now. It's within another process. So certain end users think that it is worth the ability to do that, and maybe if you have some services where that's not viable, you only deploy it on clusters where, you know, you get broad coverage, but like the data isn't as high stake. Whereas like if it's something payment related or, you know, really, really critical, you deploy that somewhere else and leave instrumentation like this off.
Thank you. Other questions? All right. Thank you, Dom.
Thank you.